So let's start to talk a bit more about what microkernels are. I mean, now we have covered a lot about monolithic kernels. Now let's start discussing what microkernel is. And a microkernel is a concept that basically started maybe 20, 30 years ago. It's pretty ancient, and it basically looked at the current operating system stacks, the way that we are designing operating systems, and it showed that, well, there's a trend that everything is going into the operating system, making the operating system bloated. And if you look at this is actually a figure that shows the numbers of lines of code in the Linux kernel over the past few years, actually over the past almost 12 years. And you see that, well, uh, it was kind of low with a relaxed definition of low, but then all of a sudden it started increasing and boom, it exploded into a few million lines of code. And this is problematic because this basically makes it very hard to, for example, establish things on how the kernel is secure, for example, to establish things on how buggy the kernel is, and so on and so forth. And again, this graph, so that people do not get confused, this is a graph for the number of lines of code in Linux. It's not for a microkernel. And basically, Windows has today over 50 million lines of code. So it's just undoable to continue like that. So the idea that the people who basically advocate for microkernels is that you should keep as much of what is not in the operating system, or basically you should keep as much as possible of your operating system outside your operating system and run it as user level services basically. And that includes, for example, things such as drivers. So right now, when you look at the Linux code that we have taken a look at on Friday, and basically during the past few videos, then the Linux code has has a folder that's called drivers. And the idea behind the microkernels is that no, drivers should not be part of the operating system. It should never be added. It should rather run as user level services. Similarly, the network stack would run as a user level service, the file system would run just as a user level service, and you would keep the operating system to a minimal. I mean, you will literally strip it from anything that is not core into the scheduling, for example, of the processes, starting processes, stopping processes, and these things. But otherwise, I mean, anything else is just outside of the scope of the operating system. And to communicate, you just need to use system calls instead of basically having the whole drivers or the network stack as part of the kernel, uh, the core kernel code. And this way, you can basically get a kernel that is just a few thousand lines of code. You can actually get it, I think, from 5,000 to 30,000 lines of code. You can get a full kernel, fully functional kernel on which you can run. And Minix is actually such a system. It started as an educational operating system. I have talked about that in a short, in the well, very lately. But Minix started basically as an educational operating system that uh, was basically trying to push this idea. Right now, Minix is no longer an educational operating system. You can still use it for educational purposes, but it is actually more, or its authors are trying to push it as a full-fledged operating system that you can use on your day-to-day life. And microkernels, while not popular for servers or for your computers, they are extremely popular in things such as embedded systems and highly secure systems. For example, in the defense industry. So if you are building the next warship or the next fighter jet, what you do is that you do not want to get Linux with its 30 million lines of code and potentially 30 million bugs in the 30 million lines of code, because, well, that's how you operate in these environments. You basically operate under the assumption that the adversary, your enemy, will just try to take control of your warship as soon as he can, right? So in that case, you want something that is very minimal and that you want to prove its security. So people in the defense industry, they don't mostly use monolithic kernels. They go for microkernels, or even what is called now unikernels sometimes. And running on these very bare minimum operating systems, they can actually go and get a few of their developers to work on actually establishing and security hardening these few thousand lines of code instead of getting thousands of developers to harden 30 millions of lines of code. And these people, for example, they used techniques such as formal methods from computing science to basically, and from mathematics also, to formally verify the security of the system. So they really take it to the edge. And some of this is actually published work. So it's actually available on the internet. It being in the defense industry, being part of what operates your war machines doesn't mean that it's a secret. It's actually, you can search on Google Scholar, for example, on things such as formally verified operating systems. And basically you take that and you work with this. Well, this is very nice, very well suited for warships and fighter jets where you have a very specific purpose for your warship. I mean, your warship is not going to change to become a game console, right? So you can optimize on this level. But microkernels suffer a huge drawback when it comes to general purpose computing things, such as, for example, your laptop. I mean, your laptop right now, my laptop is basically a presentation and recording device, but in a couple of hours, it might be a gaming console, it might be my MATLAB simulation environment, it might be my matrix computations environment, it might be just my video streaming environment. So I mean, it runs in a variety of ways. It has multiple natures, and it's really hard to optimize for these natures. Especially that in microkernels, what you do is that you use system calls to have the communication between the processes, because right now, for example, your keyboard runs as a service in user level, and that basically means that you need to do context switching from user level to kernel mode, and from kernel mode to user level to just type a single letter. And that implies that also for not just for that, if you have a couple of, I mean, if you're typewriting in your editor, and your editor basically runs as user level, and then it needs to communicate with another user level, which is basically the drivers, and I mean, it becomes a mess. Inter-process communication becomes a mess, and that takes a toll on the performance. Although some people argue that you can build things in a much better way, but I mean, that's what we have right now. Also, one very hard question is that what you can keep inside and what you need to keep outside of your microkernel. So if you have a microkernel that's going to run on your PC or on your laptop, what makes it what is so important that it such that it makes it to the kernel level code, and what is less important so that you move it outside, right? So I mean, okay, you're going to run your mouse as user level, but are you going to run your hard disk as user level? Are you going to run your camera as user level? And if you're running your camera as user level, then I mean, from one point, security becomes the problem of the driver developer, right? I mean, it becomes easier and harder in some senses because, well, it's user level, so people will try to control it and basically take snapshots of you while you're unaware. But at the same time, it's user level, and thus the driver programmer, who's someone employed by Logitech or, for example, or some camera company, will be able to actually work on it without all the restrictions that you have when it comes to Linux, for example, or the Linux development cycle, or what they impose on you as a programmer to use. So, I mean, there are trade-offs that are very hard to solve. And this is basically a summary of the philosophy that Tannenbaum, one of the most key figures in the microkernel design movement, and also one of the most key figures when it comes to operating systems research in general. This guy actually graduated most of the top operating systems researchers in the whole world, across the whole world, and he is located in the Netherlands. So Tannenbaum basically his argument goes such that when you look at your TV, you don't have a restart button. When you look at your kitchen machine, you don't have a restart button, but you have a reset button on your computer, because your computer just freezes and does nothing and goes into these infinite loops, and then it's completely useless. So his idea is that designing a microkernel should be enable us to basically build computers that are completely reliable in such a way that, well, it's user space. I'm going to kill the user space process and just continue running, because it's just user space. I mean, if the kernel breaks, it's user space. It's nothing with the actual. If the driver breaks, then it's user space. But right now, if the driver breaks and it's in kernel space, it might mess up your kernel, and then you need to restart. And with this, actually, I conclude this part of the lecture where I have talked about some different design philosophies regarding the process management, for example, what interfaces does process management have, but also some different design philosophies when it comes to basically what do you actually put in your kernel. I mean, you know that the core process management should be there, but should you put the drivers there or not, because the drivers also run as a process. And in the next part of the lecture, we're going to talk about concurrency. So I conclude that part, and I will talk to you very soon.